This is our first video on Unit 10, and it's all about the mole. So what that means is we're really starting our math back up again. And so our objectives really are going to start out with some conversions, some of the dimensional analysis that we did at the very beginning of the year. And that'll include some molar mass calculations, empirical formula and molecular formula calculations, and hydrates. But that'll be a little bit long, further down in the unit. Just for this video, we'll just kind of revisit dimensional analysis and how that's going to work with the mole. So really our focus is this first objective, just conversions between moles, formula units, mass, and particles. And that's all we'll focus on this one. So the mole is an SI unit for the amount of a substance. And you can really think of it as any other unit that we use for counting, not unlike a dozen. We know that a dozen means 12 objects. And when we're using atoms, because there's so many of them, we use a much larger number than 12, and that is the mole. So I did notice in my conversion into this software for the video, this superscript was kind of lost. But a mole is 6.022 times 10 to the 23rd objects. Now you could have a mole of anything. You could have a mole of bananas. It's just a crap load of bananas. But what we tend to use it for is obviously compound units, atoms, molecules, things like that. This number actually came from the number of carbon atoms in exactly 12 grams of pure carbon-12. So the isotope carbon-12, exactly 12 grams of it has that many atoms in it. So just so you know where the number came from. We actually honor Avogadro in that we call this number Avogadro's number. He was an Italian physicist that did a lot of work with gases and kind of was one of the early founders of some pretty cool chemistry laws. We also can use mass to figure out the number of particles with the mole, and I'm going to be showing you some of that dimensional analysis here shortly. We typically round to 3 significant digits, and remember this is 10 to the power of 23. And I would encourage you to store this in your calculator. I know that we did this a little bit in the beginning of the class, but I would recommend storing this as n. Now, I get that that seems kind of strange, but in a lot of our future equations, n is going to represent mole. So it might help you to remember later on that that's what that number represents. So I would encourage you to pause this video just for a second and go ahead and input that into your calculator. So like I had mentioned earlier, there's lots of different things that we use, or different words that we use when we count things. You could have a dozen flowers, donuts, eggs. You've probably heard of a baker's donut dozen, and that typically means 13. Maybe you've even heard of a gross, which is actually 12 dozen. But there's lots and lots of different words that we use, and I would encourage you, if you look through one of these problems and you're not quite sure where the starting point is, kind of substitute the word dozen in for mole and see if it doesn't start to kind of make some sense in what it is that they're asking for. Now, I did put this at the bottom of the slide because I kind of want to make a point here. If you have a dozen flowers or a dozen eggs, they're not going to have the same weight, and that is true also with our atoms. You could have a mole of carbon, and that would be 12 grams. You could have a mole of oxygen atoms, and that would be 16 grams. So different substances have different weights. Again, this is just counting, not necessarily measuring anything else. So in order to convert between moles and any number of particles, you would use dimensional analysis like we did earlier. So just to kind of refresh your memory, if I were to say I had 2 dozen, let's say donuts, just put DN here, and if I'm doing a conversion factor, I want to make sure that I'm putting dozen on the bottom, because if you remember, we want those units to cross out. And we know that 1 dozen is equal to 12 objects, and in this case it was donuts. So we know that we have 24 donuts. So a mole would work in the same way. If I had 2 moles of donuts, okay, I would put a mole down at the bottom here, and I would put Avogadro's number on top, 6.02 times 10 to the 23rd. And just means we have a lot of donuts. 1.20 times 10 to the 24th donuts. But it works the same way. We want, if we have a mole on top here, we want to make sure that we're putting mole on the bottom of the next conversion. So I have a couple of example problems in your notes, and one of which says how many particles are in 3.5 moles. So I'm going to start with 3.5 moles. And again, the next conversion factor, I want moles on the bottom. And 1 mole is equal to 6.02 times 10 to the 23rd particles. Moles cross out, and 3.5 times this number gives me 2.107 times 10 to the 24th. But if we look, we have 2 significant digits in the beginning, which means we're not going to include those 2 right there. So we would have 2.1 times 10 to the 24th particles. How many moles of atoms are in 9.63 times 10? That is to the power of 26 atoms. So I'm going to start with that number, 9.63 times 10 to the 26th atoms. And this is going to be flipping my conversion factor upside down, because if I'm starting with atoms, I want atoms to be on the bottom. And if I'm going to moles, I want moles on top. So my atoms are going to cross out, but in 1 mole, I would have 6.02 times 10 to the 23rd atoms. And I'm going to plug this into my calculator real quick. And I get 1,599, which I'm going to round to 3 significant digits. And if you look right here, and I kind of did this on purpose just as a reminder for significant digits, if I rounded this up to 1,600 without a decimal point, I would only have 2 sig figs. If I rounded this up to 1,600 with a decimal point, I would have 4. So your best bet is to use scientific notation. And this is how many moles I have. So if you noticed, I moved my decimal point over 3 places, which is where that exponent comes from, and I have 3 significant digits because that 0 counts. All right, now we're going to include molar mass with the conversions with the mole, and this will be the last section that I do with this video. So molar mass, if you remember, is just the mass in grams of any 1 mole of any substance. The units before that we were talking about were in AMU, were atomic mass unit, but they happen to be equal to a gram per mole. So when I first introduced the idea of the mole, I said that the number of particles in a mole were equal to exactly 12 grams of carbon. So what we say is carbon is 12 grams per mole, because if I had a mole of carbon, that's how much it would weigh. That would be the mass of it. So on the periodic table, we can consider it being listed in AMU, but it is also listed in grams per mole, which is kind of convenient for us. So any of the masses that you need for any of the elements, you just get on periodic. A little fast there. Example problems 3 and 4. If I need 3 moles of copper, how would I measure that out? Well, if you need 3 moles of copper for an experiment, okay, we're going to start with 3 moles. And I know I want moles on the bottom, but if I'm measuring something out, it's not like I'm counting these things. That means I'm going to use probably a scale or something, which means I'm using mass. So I would put the molar mass of copper up here as 63.55. And I didn't memorize that number. That number's from the periodic table. Notice my moles cross out, and that is the mass of 1 mole of copper. So I'm taking 3 times 63.55, and I would go over to the scale and I would measure out 190.65 grams of copper. Again, I notice I have 2 sig figs up there, so I would take this to 1.9 times 10 to the second, or you could just say 190. I'm okay with that, either way. But that's how many grams of copper I would scoop out into my massing dish for my experiment. And so I'm going to turn this around for the fourth example problem. If I measured 5 grams of iron, how many atoms do I have? So I'm going to start with 5 grams of iron. And for me to go from grams to moles, I know that I want grams on the bottom and moles on top. So I'm going to look on the periodic table and I'm going to look up the mass of iron in 1 mole. My grams are going to cross out, and this time I'm going to take 5 grams divided by 54.55, and this is going to tell me I have 0.0916 moles. Now notice I answered the second half of this question. Now I know how many moles of iron I have, but I also want to know how many atoms are in that. And if you look, moles are kind of in the middle of this dimensional analysis problem. I'm going from grams to moles, and then if I want to go from moles to atoms, then I need another conversion factor. I'm going to have moles on the bottom, and I'm going to have Avogadro's number on top. My moles cross out, and I'm going to take my previous answer and multiply it by Avogadro's number, which I had stored as N, and my answer, my second answer for this question is, with 2 sig figs, 5.5 times 10 to the 22nd atoms of iron. Now, a couple things I want to point out here. From the example problems 1, 2, 3, and 4, what I want you to see is moles are kind of the central figure to all of these calculations. If I want to go from atoms to mass, I need to go through moles first. So right here, I started with mass, and I wanted to go to atoms. I had to go through the mole before I got there. I kind of like to think of the mole as a central station. You have to go there before you can go anywhere else. So kind of think of that as your first go-to, and you might get tired of me saying this, but in a lot of our example problems, I'm going to ask you, so where do we go first? And the answer is almost always, well, we go to moles first. Table. Nope. So in our notes here, I tried to make kind of a summary here. If we start with moles, you're going to use our molar mass from the periodic table to go to grams. If you start with grams, you're going to use the molar mass from the periodic table, but it's flipped. So that's one way of looking at it. Now I'm gonna just show you a couple of other example problems before I wrap this up, and then we will discuss this further in class later this week. How many atoms of gold are in a U.S. Eagle bullion coin with a mass of 31.1? So I have 31.1 grams of gold. And you should put grams on the bottom. And if I want atoms, and this is what I was kind of saying earlier, that you want to make sure that that you're putting grams on the bottom, and you're going to go to moles first. So you're going to want to look up the molar mass of gold and put it down here, and put 1 mole on top here. Your grams are going to cross out. And I have one more step here, because now I'm just in moles. My grams crossed out. Now I need moles. And I'm going to put 6.02 times 10 to the 23rd on top and put 1 mole on the bottom. Now I'm going to have you finish this one off on your own, and we will double check your answers when I get back. Now, the next one that I have here is the mass of this many atoms of lead. So again, notice I'm going from mass to atoms, which means the center point of my conversion factor is going to be moles. And again, this is to the power of 15 here. 5.8 times 10 to the 15th atoms of lead, which is PB. And so this one's in the reverse of the one that I had as example problem number 5 there. I'm going to put atoms on the bottom, and I want moles. So I want to go to moles first. I'm going to put Avogadro's number, or N, in your calculator on the bottom, and 1 mole on top. Then, now that I'm out of atoms and I'm in moles, now I can go into grams. So again, I want you to look up the mass on the periodic table for lead in 1 mole. The moles cross out, and I want you to again try and get these two numbers, and we will confirm on Monday, or sorry, on our block day to make sure that you got everything correct, and we can double check any questions you might have. So anytime that we're calculating molar mass, when we're just doing that of just elements, it tends to be kind of easy. But if we have something of, say, a compound, let's say I have copper chloride, I would need to look up the mass of copper, which is 63.55, and I only have one of those, plus I have 2 chlorines, and that is 35.5 grams. So I would have to add those all up to get the molar mass of that compound. So this is yet another conversion factor that we can use. So once I add that all up, I'll do that real quick here. I have 63.55 plus 71, I would have 134.55 grams per mole. So this is now a new conversion factor. I could put 134.55 grams on top over a mole, or vice versa. But this is now my new conversion factor. So my last 2 example problems just really want you to see if you can figure out the molar mass of a compound. So in this case with water, I know that I have 2 hydrogens and 1 oxygen. Hydrogen is 1.01 grams per mole, and again I get that off the periodic table, times 2. And I have 1 oxygen, which is 16 grams per mole, and I only have one of those. So I would add those up, and I would get 18.02 grams per mole. So I would like you to try these other 2. And again, I'll post those answers, but I want you to try those 2 on your own. I don't want this video to get too long. And I've got 3 more here. Again, if you feel like you've got the concept, you don't have to continue to do these, but if you feel like you need the practice, it's certainly not a bad thing to try. So things, again, to keep in mind, I use this kind of visual just for some of our visual learners in the class. If I start with a mass of a compound and I want to go to the number of particles, moles are always the center thing that I'm going through. So just kind of keep that in mind. If you're given atoms, go to moles. If you're given mass, go to moles. It's your central station to get any of the other compounds that you might need. So the last thing that I've got here for an example problem is what is the mass of 2.5 moles of C3H5, in other words, I have 2 of this group and a sulfur on there. So I'm going to start with 2.5 moles, and I want to go to mass, which means I need to know how much what is the mass of this compound. So I need 3 carbons, 5 hydrogens, and then I'm going to take that number and multiply it by 2, and then I'm going to add a sulfur to it. So 6 carbons, that's 12 grams times 6 gives me 72. And I've got 5 times 1.01 for hydrogen, which gives me 5.05, plus a sulfur, which I believe is 32. So if I take all of those, 72 plus 5.05 plus 32 gives me a molar mass of 109.05 grams per mole. So if you look here, if I'm starting in moles, I know that I want moles on the bottom, and I'm going to put 109.05 grams on top. My moles cross out, and I'm going to take that molar mass times 2.5. My final answer will be 272.625, or at least that's what my calculator tells me. And I have 2 sig figs, which means I can round this to 270. I hope this video has been helpful. We will pick up where this left off when I get back, and good luck.